Hello and welcome to the second tutorial on the simple manipulator control library. In this video we'll go over the code as promised in the introductory presentation, and the code that I will present is the core functionality of the library. Some of the basic use, of course, and some of the things you would typically use for quality of life. In future videos, I will go over some of the examples in more depth, go over the math, and then show the examples in code for what exists already. This will culminate in a video in which I sort of in a live stream type of way develop one of the control loops that I would want to add to the library, so that you can see the whole process in action, not just see what exists already, but the process of actually using it. I think that would be the best selling point. After that, I will also provide some videos on the libraries that I heavily use within my library, namely Pinocchio for the dynamic computation. And you will want to learn these libraries as well in order to, because my library so heavily relies on them, if you will want to do something a bit more advanced, or if you would want to help me in the development of the simple manipulator control library, which I would very much appreciate, if you're interested, of course. Okay, without further ado, let's start. So basic use, we'll just run the simplest possible example to see this in action. Yeah. So right now I'm at home, so we'll be running this in simulation, but later on we will run this on the robot so that I can sort of prove that it really runs the same way as advertised on the real robot. But anyway, let's start. There we go. So I will be running the Docker image that I have provided where I shipped the library. Please, I refer you to the Docker tutorial within the Linux series of tutorials, within this wider scope of tutorials on the introduction to software and robotics, to see how you would install Docker and build this image. So now I'll just run it. And here we have the repository ursimple control. That's the sort of old name for the simple manipulator control library. I will change this at some point. But anyway, what we're interested in here is Python. The Python, and in this folder, the library, the Python library, as I said, it's in pure Python, is defined, particularly over here. For our purposes now, we want to just run an example. Oh, I just remembered I didn't enable the Docker to interface with my graphical user interface, which we need. Okay, so here are some examples. The simplest possible one is clik, where we run point-to-point closed loop inverse kinematics motion, not even with orientations, but just positions. And what I want to advertise here is that if you run on this example or any other example, the -- help option, you will get access to all of the different functions that you can add, and every single magic number. So the idea is we want to get rid of all of the nonsense, let's say, in the code to make it as easable to read, but also to change it as much as possible, because of course in control, tuning is a huge part of what we do, and we have to have a way to do this in the most painless way possible. And you also have some documentation for what these different options are. They will be mostly the same across different examples, because some of these are obligatory. Once you start developing your own functionality, I suggest that you simply copy-paste these ones. So rather you take one example file here, and then you sort of you take out what you don't want and add your functionality there. That would be the simplest possible way to get started. But anyway, let's run this thing. And since we're in simulation, we definitely want to visualize the manipulator. We also want to do real-time plotting so that I can show this immediately. And we want to tell it to run in simulation. For this, we say Pinocchio only. Pinocchio is the library I use for my library uses for dynamics calculations or kinematics at this stage. But they support dynamics as well. That's how they will be implemented as well. Anyway, let's just run this. Okay, so we run the script. The visualization for the manipulator will happen in the browser. So I will quickly bring this down here. Okay, as you can see, so we're running it on UR5E with the Hand E gripper by Robotic. There's no color here. This got patched in Pinocchio 3.2 that I typically use, but since we're only installing Pinocchio via pip here in the Ubuntu Docker, this is Pinocchio 2.7 and it has no colors. But I mean, doesn't really matter, it gets the job done either way. The real-time plotting will start soon enough. So here we enter the target and effector position in this format. All right, and let's run it. So as you can see, it changed. Of course, the gripper went through the body because we don't have any collision avoidance. So this is just the pseudo-inverse, damped pseudo-inverse running, and yeah, the position where it was, the orientation doesn't change. You can add it, but in this particular example, it's just less typing. And this is sort of just the example to verify that everything works. And before continuing any further, we're now in the robot lab, where I will quickly demonstrate that you don't need to change anything with the code in order to be able to run this same script. So here's the robot. Here's me. I have my hand above the big red button to stop it if anything changes. Anyway, we run the Docker. We navigate to Python examples. We run Python 3 clik. Now I won't run any of these other arguments because there's no need for plotting and visualization. I have the robot next to me. Press the enter here. Now I'm connected and so on. This will be explained later on once we go to connecting to the robot itself. Okay, it's complaining. That tends to happen. I will simply run the script again. Okay, so now the difference is that it is giving me the positions in the base frame for the tip of the end effector, where the first three numbers are the linear positions in the base frame, and these are the orientations. Now this script, as mentioned, does not change the orientations. Does now allow us to put something else in. Now I will do a very small change. This was what I want to give the print out here. Let's, I don't know, put this to 3, put this to -0.3, and put this to 0.5, let's say. Okay, my hand is on the button as I start running the script. Very important to be safe. Now, in fact, we even don't let you run this yourself if you're a student here. But since I'm an employee, they do trust me, and it says so on the door. Okay. And there we go. The robot moved. It's a very small movement, but that's completely fine. That's what I wanted. Just simply to demonstrate that it works. Again, there's no collision avoidance, so it's not advised to just put in any old spot here. Okay. Okay. Now let's go on to the core functionality. Now, there's two main classes that are used here. This one will be, in a future release, will be turned into an abstract class and then specialized for every single robot. Now we just have ifs to change things inside, as I'll show you for now. But before we jump into the code, let's have an idea of what we will be looking at. So the job of this class is to handle the communication with the robot for you. You use some predefined, you use some wrappers around the socket that communicates with the robot basically. And the idea for when this will be ported to other robots is that you just swap the different drivers for communicating with the different robot that you have. But as you'll see, we only rely on simple functions that literally every single driver simply has to have implemented. Otherwise, it doesn't do anything really. Okay, but this is sort of hidden in a nice small layer that you can, of course, check out to see what it does really. And if you run the function step by RobotManager, it will also, it will get the latest updates, put this into the variables of this class that you can then access through simple getters. Because it's just sort of to ensure that you don't accidentally make mistakes with the code. It's better to use a getter, even though Python doesn't have private variables, but these internal variables of this function would all be private otherwise. Anyhow, and the dynamic or kinematic computations are also done for you so that you don't accidentally forget them. So things like forward kinematics are run as soon as the new joint angles are obtained. And yeah, for typical functionality for this class, you would use just step and the getters. Anyway, let's jump into this. Now simplest way to get it is to simply jump to the definition. Now I can't stand that this is slightly in bold, and as you could have probably seen if you're following along these tutorials, of course everything is here written down in a completely readable way, but I can't stand the fact that this is in bold, so I will actually just exit the Docker to go into my normal setup, and this is the exact same repository. In fact, the Docker file was built from this, and simply the directory has been copied. Okay, this lies in the manager's file in the simple control directory. Now, of course, the first thing you will see, there's a bunch of to-dos because this is work in progress. And let's actually go over the prints. So, in particular for I use URTDE library to interface with universal robots that implements their application protocol layer communication, and also the lower level with the managing of the messages. So how do you splice the messages correctly and so on, the packaging. Okay, it runs at 500 Hertz, which is good. Anyway, what we want here, and as you can see also, I try to document the code itself as much as possible. Anyway, we want RobotManager. There we go. Okay, let's see what it says here. Rely on Pinocchio as much as possible while concealing the obvious bookkeeping. I think this does, in fact, explain it quite well, but now you have... Okay, so ControlLoopManager is the other class that comprises the core functionality. What it does, it handles the bookkeeping around your mathematical expression that is your control loop. But you write the control loop that you have as a function, you put it as a sort of a partial. I will immediately go over into this, then you put it to ControlLoopManager. So let's see how that would look in particular. Okay. So let's say you had clik. We'll go over this program too in more detail in a different video. We're now just I just want to give you the rough overview of the core functionality. But anyway, let's go to the definition of this CompliantMoveL. So there's two steps to it. First, you have your sort of mathematical set of, your math in the loop. Now, unfortunately, it's not a single line because you still need to do other things to it. Here we map, we get the range, we map it into a different coordinate frame. Won't get into it too much. We do something, we scale the range. This is the CompliantMoveL, so we want to be soft with respect to the external forces. There's some place where we want to move, we compute the error and so on, we get the Jacobian, and here is the actual line of math that is your control loop. And here we send the speeds as well. That probably shouldn't sit in this class, but this is all work within this function, but this is all work in progress. But it doesn't really matter if it's here or not. I think I maintained it here because I wanted to see it. We'll see about the details. I'm very open to different opinions in design, because I'm, as a sole user, I sort of put everything as, what made sense to me, but that's just me. Okay, and then we have to say what we want to log over here. All right. So this is the control loop compliant click. Now we have the CompliantMoveL class that would actually create the control loop with the ControlLoopManager around this particular function. And this is not what we actually are interested in here. We just want to get the, so this would run it as well. That's why it's a single function anyway. ControlLoopManager is what we're after. So I wanted to show you the first line of math. Let me first not get sidetracked. So it does the book. So this function, this class, will do the bookkeeping around this one line of code that your mathematical line of code. Of course, you have to do some computations to get the Jacobian and so on, but there's some other bookkeeping going on around this computation itself. Okay, it wasn't too bad. Let me just make my face a bit smaller. Okay, so this class will, among other things, ensure that the timing is right, so that if ideally your control loop is finished before the allotted time within the frequency of the robot. The UR5 runs at 500 Hertz. It will also do some managing for the visualization and plotting, as that has to happen around while your control loop is running. Otherwise, there's nothing real time about it. And it ensures the killing of the program as well. So these are the topics that we now want to see in the code itself. Okay, so what you pass to ControlLoopManager is the RobotManager, as some of its functions will need to be called here. The control loop that you have, so that's your math. And finally, some of the arguments. And to tell it what to log, you also need to give it an example of what you want to log, basically. This is in case you want to use previous values. 5, 10, 20, whatever number of time steps before the time steps of your the execution of your control loop, because you might want to do some filtering on some signals that you have going on there. Okay, so we just instantiate all this. We create a way to have DQ is just how your this window of the things that you want to pre-save for signal processing. So for example, you have your 4-star readings, they're very noisy, and you want to get access to the previous 10, let's say, so that you can do a low pass filter on them or whatever else. Here we create the logging that's all in dictionaries, then lists inside, because I mean they're dynamic lists, but they have O of 1 time for addition at the end, and then only later do we turn them into numpy arrays to be saved as logs. So the entire run, whatever you wanted to save, that's why you pass with these keys. Okay, so there's some printing going on if this will be turned into logging. There's some multiprocessing going on for the real-time plotter, because we want we want to handle this here basically. Okay, this is what's important. The run function, where you run your control loop until convergence or until a final iteration. So this is not a while loop, simply as a precaution in a way that once this will be turned into a while loop eventually. This was in fact so that I don't run out of memory from adding too much in the lists, because I don't automatically delete them. That's again nice sort of a quality of life improvement that I want to add to the library, but it's not a priority, so it hasn't been added yet. In any case, we call the step here so that you don't have to do the forward kinematics or stuff like this yourself. Then we have the control loop you passed that takes in whatever you sort of wanted. So if it requires multiple arguments, you sort of shorten it to this form with a partial function. I should actually let's immediately show this. Yes, so your control loop clik here, it had the arguments that I don't think are even used. It requires the RobotManager as well. That's all passed by reference, so it's the same ControlLoopManager. Anyhow, we want every single control loop in the ControlLoopManager to just take in the time step and the past data. So we basically say, okay, turn this function and turn it into and pre-assign these two arguments already, so that only the rest are called. Only the rest are used if you use the control loop function. So takes a function, the result of partial is a different function that simply has less input arguments, because you pre-allocated some of them here already. Anyhow, so ControlLoopManager, that's how we ensure that ControlLoopManager runs for every single control loop that you pass it, not regardless of the arguments it takes, so that we don't have to have different kinds of that you don't have to change this for every different control loop that you have. And it expects these return values. So do we need to break or exit this big loop, and what to save in the window for the indeterminate, for the small number of past values for things like filtering, and what's the log item, and these don't have to be the same, of course. Okay, and now we handle the past data, and that's in the queue. We put in which simply append every log item, and now this potentially should be an argument as well, but I thought that from my experience the 20 worked so good that it didn't need to be changed. So we both visualizers run as separate processes, and we simply put the latest value into the queue that they read, the multiprocessing queue that they read. So, if they have the time to execute the visualization, great. If not, who cares? The point is that this does not affect the time required to run your control loop. And we also don't want to, for any sort of waiting to be happening while the other process is reading from this. Okay. We just put the latest things to plot in the queue. and you can select what's plotted is selected is the same as what's being logged, essentially, because the idea is that that's what you want to see. That's why you're logging it. I didn't want to complicate things more by separating this as like visualizing thing and the logging thing. Okay, and here we take care of the frequency, which is extremely simple. So end time, start time, you minus this, and we sleep for the rest. If the deadline is missed by some number of time, that's what we report. If you selected that you care about reporting this, all of these is simple control loops run. They have a bunch of time to run. Now there are some misses every so often, but they've never seen more than like 1 or 2 cycles missed at 500 hertz. So I think we're fine. But like I said, no real-time guarantees. Okay. And finally, we need a function that runs if it's killed. Now this is so long that we in fact need to see with a ruler of sorts that where the run function actually ends. There's even a return. Okay. So that's it. But basically, yeah, if the for loop has ended, that's what we wanted. Yes. So if the for loop ends, then we print something out basically, and we tell the real-time plotter process to die. Okay. And now we have the stop handler. So if at any point you want to stop the execution of your current control loop, if you hit the stop button on your robot, it will violently stop and break, and this will basically give it some time to slow down before that happens by sending 0 velocities. Now these 0 velocities they don't happen immediately, of course, because there's an inner control loop that sort of turns this velocity command into torques. We don't have the access to that, of course. That's performed by the robot. And then, we also, so for the UR robot, you in particular want to stop by free driving. Now this could have also been a function that's defined for the particular, for the RobotManager. I decided to put it here in the end because for one RobotManager you can have, I don't think it really matters, but I ended up putting it here. Could be changed. And so we kill the processes. We plot the final log if you logged something, and that's really it. Okay, so that was that. And with this, we covered the 2 main classes that comprise this library. They're all in the same file, and this file in total is it's very short. Not even 1,000 lines, with all of the documentation as well, mind you. So it's incredibly short. I definitely implore you to read it if you're wondering about something. If there are bugs, please go in there and tell me about them. There certainly are at least some. Okay. And now let's discuss some of the quality of life functionality as well. So we have the basic control loops. This is essentially joint space controllers. We have the Cartesian space controllers, so closed loop inverse kinematics, and we have a bit of functionality in the convenience toolbox. That's things like setting your robot to free drive, things like that. There will be some remote input added there eventually. I mean, there is a program for that for the UR5 robot, it's just that it has to be fine-tuned a bit. And then we have visualization as well. But let's first go over these premade loops, just so that you see what exists already. So in the basics, we have the moveJ command, and that's in fact it. There's a single command. I simply didn't have a need to define another one, so that's where we're at. If you want to do joint movements in joint space, they're here. One example function that should be added here is CompliantMoveL, of course. That might be a candidate for what we want to do in the live demo, for example. Later on. Now we have the point-to-point motion for clik, and that should be merged with the other file as well. Here we have some of the predefined controllers for inverse kinematics, like doing a QP, a pseudo-inverse, a Jacobian transpose. And they're sort of predefined, they're defined in separate places, because for different control loops you want to use this same stuff a bit more times. Here we simply turn from an argument into just assign a different function for it, because that you can't do that with the arguments. There's other ones that I will add eventually, just didn't have a need for it yet. Here we have the control loop clik, which, oh, this is not necessary anymore. The thing that I noticed. Yes, that will be pushed immediately. Anyway, we compute the error. We get the Jacobian. That's probably also good to put into step and then have a getter for it. Do put in step, have getter for it. Okay. And yeah, that's so it computes the joint velocities and sends the speeds. The other stuff that we have is like move until you sense something, so move and stop if you don't know where something else is. So that's move until contact. Again, there's the actual control loop with the math for it given here, and this is not needed. And it just stops. This one just stops if there's some sort of a force. Okay. And then because we want to have it just, if you ever want to do this, you can just use this function and the robot will go in the direction of this argument. And that's it. So that's why we have two functions in the library for these predefined functions. We have the MoveL, of course, the CompliantMoveL, and yeah, that's what we can see here. And here we would have just the clik that's used for following a Cartesian path, and this will in fact get you return the whole of the path, so that you can use a joint space controller for this. That's what we have here. There's some DMP stuff where, in particular, if you give it the only thing I use it for is if I give it a joint space trajectory, it computes a DMP around it, a single one, but that's sort of a bit easier to have a controller with that. And in util we have some smaller utilities like calibrating a board and a bit of the freedrive stuff and so on. That's copy pasted from the convenience toolbox, because eventually these things will have to run for separate robots. Whereas in the convenience toolbox, they're defined with raw UR5 driver commands. Okay, and the final thing we want to touch on is the visualization. So what you saw in the beginning where we ran the example is meshcut, and that runs in the browser. You can add more things to it if you wanted, some objects and stuff. You could turn the meshcut into a whole scene visualizer. I will go into stuff like this once we get to the videos on these particular libraries that I use. The real-time plotter that you saw was just matplotlib. We had a matplotlib tutorial already, so if you want to see this, you can. And finally, we have logging via pickling. So You've seen in the control loop class that everything that your control loop function returns is just put into one big dictionary of lists. Those are turned into NumPy arrays, and that whole thing is pickled along with the arguments that you ran. So that's how you would log a run to analyze it later on, which is especially useful for comparisons or if you want to make some graphs comparing different algorithms and so on. And finally, we have like this, the visualize, the manipulator motion, visual motion analyzer that you saw if you saw the tutorials on other Python packages and matplotlib. But basically this is it. It's a bit ugly, I know, and here we can sort of compare different inverse kinematics algorithms. But the idea here is there's a setting in this program that I won't fish out now because it requires me to change a bit of code, because I very rarely use this, so I didn't make it particularly usable. But the idea is I will add, the parameters and everything there. The idea is that you can put in a log file into this, or multiple log files, and then compare them in this interface, which is a bit easier to use than to just have, two sets of different graphs side by side. Now this definitely needs to be expanded to support your various logging, the logging that happens in the real-time visualizer. As you saw, you might have, you haven't seen this yet, but you can pass whatever logging you want as long as it fits on that sort of the 3x3 matrix of plotting graphs. If there's a demand for it, I will put that in the right side over here, so that automatically all of your logs are put into this, and the additional tabs, if necessary, are generated. It would be very good to have this, instead of having this very simple representation of robots, to either be made a bit more pretty, or alternatively to run Meshcat alongside it. And I mean, as you saw, all of the components for this exist already. It's just that, it takes time to code these things up, and I have science to tend to. And this is the quality of life sometimes suffers for science. Not a lot, of course. But there's only time for so much. Okay, I know that this was sort of this was a speed run of the core functionality of the library, but I hope that I at least convinced you that it is very easy to read and to get into, and that it does the things that I promised in the introductory presentation. Now, of course, now you saw the skeletons in the closet that are all of the different to-dos and the unfinished things. I am, of course, working on this. If you are using this library, if you're not just me, please send me emails with with your potential improvements, with the things you want to develop if you want. That's I will certainly, especially if you're a student that is taking a project with me, I will immediately run to your help. I have allotted time for this specifically. So this would be priority. If there's something buggy in the library, just please send this over to me. I know that I'm taking a bit of your time instead of giving you completely clean software, but I think you will get to your goal, and you will help me tremendously in developing this for hopefully mutual benefit, because it's difficult to know in advance what people want and what breaks if it's being used in a different way. I can't generate all of this from my head so easily. Okay, but I hope you learned something with this, that you're inspired to try it out, to do something with it. And yes, do check out the following videos to get more in-depth usage examples. This was just an overview after all. But if you are feeling confident that you can just go ahead and try things, absolutely feel free to do this as well.